Hello everyone, and welcome to this latest webinar from IHS Markit titled 5G X-Haul for Network Density. Today our panel will explore how mobile operators can transform their mobile transport networks to an X-Haul architecture that supports the demands of dense and diverse radio deployments and delivers the performance capabilities needed for 5G. Our webinar is co-presented by IHS Markit and our partners Anritsu and Fujitsu Network Communications. My name is Alan Tatara, Senior Event Manager for the IHS Markit Technology Group webinar team, and I want to thank everyone for joining us. Before we begin, I want to highlight some of the features that are available to you on our webinar. So the console that you're looking at is completely customizable, so you can open, close, move, or resize any of the windows that you have open on your screen and arrange the console as you like. Now, at the bottom of your console are several application widgets which contain additional features available for you. One button I do want to call out is the resource widget, and this is where you're going to find additional material about our topic, including the downloadable slide deck from today's session, as well as other valuable information, including a special report authored by analyst Richard Webb. So make sure you check these out during the webinar. You'll also notice a Twitter widget at the bottom of your screen. This means you'll be able to tweet directly from the console, and today we're using the hashtag 5GNetwork. We will also have a live Q&A session directly after our presentation, so please submit your questions or comments at any time by using that Q&A box that you see on the left side of your screen. Also, this webinar is being recorded, and the on-demand version will be sent to you within 24 hours. And if you encounter any technical issues, just click on that question mark widget, and you will get the answers that you need. So now let me introduce our panel. First leading our discussion is Richard Webb. Richard is an Associate Director in the Mobile Transport segment at IHS Markit. We are also joined by Stuart Whitehead. Stuart is Senior Product Marketing Manager in the Optical and Transport Solutions Group at Anritsu. And rounding out our panel, we have Joseph Masarino. Joe is Principal Solution Architect in the Optical Networking Group at Fujitsu Network Communications. So welcome to our panel. It's a pleasure having you with us. So let's get started. Richard, I will pass the controls over to you.
Thank you very much, Alan. Hello, everybody, and thanks for joining us. So as you can see from the agenda on screen, I'm going to start with a few introductory comments, and then we'll dive into some of the problems and challenges of adding 5G radios to create network density. And this will be followed by an overview of some of the options and solutions available for backhaul, midhaul, and fronthaul. Then we'll review what this looks like from various deployment perspectives. We'll briefly hear our sponsors, Anritsu and Fujitsu, talk about their approaches, and then we'll make a few quick concluding remarks before we enter the Q&A section. So, without further ado, let's kick off. So I'm going to start today's webinar by briefly giving some context around 5G. As you see from the slide on screen, 5G is well underway, as I'm sure you're aware, and that is really as a consequence of widespread industry participation from standardization bodies, industry associations, working parties, vendors, operators, service providers, all across different parts of the component, equipment, and devices ecosystem. And this is, of course, across a global perspective. But what does that mean in terms of the radio network specifically? Well, here we have a bit more detail on screen about the readiness of 5G new radio, both in standalone and non-standalone mode based on next-gen core network and the enhanced packet core network, respectively. And really, this slide is just to emphasize that this is happening now and that operators need to position themselves both strategically and technologically if they're going to be able to take advantage of 5G services and the potential new revenues that they could generate for operators. But to do so, mobile network architecture is going to have to go through a new phase of evolution, and it's going to look somewhat different from previous iterations and generations of mobile technology. One of the network domains that requires attention is the mobile transport network, and that's what we're going to be really focusing on in detail in this particular webinar. But before we do that, I want to spend just a few minutes focusing on some of the characteristics of 5G new radio, because these impact the transport requirements and the architecture of that mobile transport network into the 5G era. So firstly, 5G new radio supports brand new swathes of unused spectrum from very low to very high frequency bands. That's, for example, from 400 megahertz to 100 gigahertz with ultra-wide channels. In existing bands, channels are 5 megahertz up to 20 megahertz wide. Above 6 gigahertz frequencies, channels can be as much as 100 megahertz, and that in turn delivers huge multi-gigabit throughput and very low latency requirements. Also, 5G brings a set of different scalable and mixed numerologies for optimal operations in different frequency ranges, with numerology being defined as the OFDM configuration in terms of things like subcarrier spacing and clock frequency. Also, in order to achieve ultra-high data rates while supporting ultra-low latency, the industry has agreed to adopt polar coding for the control channel and low-density parity check for the corresponding data channel. On the RAN side, architectures can be more flexible and more modular, and this allows for a split in the base station between the control unit, also known as the baseband unit, and the distributed unit, also known as the remote radio head, which includes a subset of these functions. We're going to see Ethernet likely to replace the current CPRI protocol for the Fronthaul connectivity between those two now split units, and we're going to hear a lot more about that in the rest of the webinar. And finally, there's support for network slicing, also something we're going to be looking at in more detail as well. So hopefully that frames a little bit of the discussion to follow by highlighting some of the considerations for network architecture, those being in terms of things like capacity, latency, network density, and some of the other performance requirements. But before we move on into the meat of the webinar, really, I just wanted to share a short data excerpt from one of IHS Markit's research reports. This chart on screen is taken from our annual mobile service provider survey focused on 4G to 5G evolution. In it, we asked a selection of 20 or so decision makers from mobile operators around the world to share with us some of the insights that they could into their network strategies and their technology decisions. And in this particular question, we asked what was driving their move to 5G. So, as you can see on screen, there's a variety of very strong drivers, including gaming, video, IoT services, but really the prime driver is the ability to offer enhanced or extreme mobile broadband services. And really it's with that kind of network density to allow that kind of service that we're going to be focusing on within the webinar today. So to tell us a little bit more about this evolution and the role of X-Haul within it, I'm going to hand over firstly to Stuart Whitehead of Anritsu and then Joe Mosserino from Fujitsu, who will follow on by talking about some of the challenges for Fronthaul, Midhaul and backhaul. But Stuart, we're going to start with you. So over to you first.
Excellent. Thanks for that, Richard. So first of all, I think we need to just quickly have a look at the history and why we need to replace the wired connections and so forth. If we have a quick look at CPRI and the actual throughput that's possible on CPRI, for example, the top right picture there, a 10 gig or rate 7 CPRI connection will give an actual end user throughput, you know, his web surfing, etc., of something around 600 meg. So when we look at that, we actually get a throughput rate of in the realm of 6% of the actual line rate. CPRI, of course, has a lot of other data in it that's used. It's not wasted data, but from an end user perspective, the efficiency is actually quite low. So what we want to do here is concern ourselves with how do we improve that. The next point with CPRI is it's quite restrictive on the distance, and that's another thing that the standards bodies have looked at to improve that is by being able to get more than 15 to 20 kilometre distance in the mobile Fronthaul across the mobile network section. And that's been achieved by different areas we'll discuss going forward. So one of the key things that's come up here is 3GPP standards group have defined what they call the functional split. And the functional split is all about how much resource or processing power we put in the RU compared to the BBU. So looking at the bottom diagram there, we can see that option 8, which is CIPRI as it is today, we just have the RF green section in the RU. But if we were to move to option 7, we end up with the lo-fi as well, and so forth up all the way to option 1, moving more resources into the radio unit. This is done mainly to allow better throughput in that and make that efficiency that CIPRI didn't have, make the future network more efficient by putting more processing in the radio unit. So for option 7, which is commonly used for option 7.1 or 7.2 split, commonly used for the mobile fronthaul area of the network, we get about 3 to 4 times more throughput. Whereas if we look at option 2, which is commonly talked about being used for the mobile midhaul area, or NGFI2. So it's all about getting better throughput for the network and more efficiency in that fronthaul connection. With that, I'll hand it over to Joe to continue.
Well, thank you, Stuart. So let me talk about fronthaul challenges. In establishing a centralized RAN network, there are benefits of high performance, bandwidth allocation, and flexible network engineering through cell site aggregation and pooling. With these benefits, there are numerous challenges in the deployment of a fronthaul network. For the 4G LTE fronthaul, there are many high-speed channels, typically operating at 10 gigabits per second each, and that must be maintained with a latency budget of up to 100 microseconds. The 5G fronthaul network has a different BBU, making it an overlay onto the existing 4G LTE environment. To transport these two networks, the service provider needs a lot of dark fiber. In areas where dark fiber is limited, a multiplexing solution is needed. Traditionally, the multiplexing solution is based on WDM technology. 4G channels operating at 10 gigabits per second rates or lower, but the new 5G rates are up to 25 gigabits per second, and based on the capacity of spectrum available, can have up to 2 25 gig channels per radio unit. Now realize there will be multiple radio units at each one of these cell sites, depending upon the sectors and number of antennas and channels as well. DWDM optics at 25G are just coming onto the market for the first time, and therefore will have a high cost. This will also challenge footprint and power requirements at the cell site. The midhaul and backhaul segments of the network will also undergo a major change. With multiple use cases envisioned for 5G traffic, the point-to-point and point-to-multipoint network will evolve to an SDN mesh network with virtualization. Traditional routers will be challenged since they are comprised of an integrated control and user plane. They may have several chassis size options to support different capacity versus cost requirements, but the chassis limits will dictate their scalability limit. This is referenced as scaling up to a limit as defined by the chassis and integrated control and user plane capacity. An initial network deployment using a traditional router will consist of control and user modules in a chassis that is typically 20-30% utilized. But the operator will still have to allocate the maximum footprint, power, and thermal reserve for that platform. Then there is the performance per capacity risk of over or under engineering each site. Deploy a platform too small and not meet demand, or over-engineer the site, resulting in inefficient CapEx use. Essentially, an integrated control and user plane router platform scales up to a limit, which results in inefficiencies and potential lost revenue opportunities. Let me hand that over to Richard.
Thank you very much, Joe. So we've heard some of the challenges of this evolution in the transport network from 4G into the 5G domain. But what about some of the solutions? This time, to start us off, I'm going to ask Joe to tell us more, particularly about the characteristics of Ethernet and how that will change the dynamic in the Fronthaul domain. So, Joe, back to you.
Great. Thank you, Richard. Well, the IEEE has defined a series of standards via the 802.1 working group in support of time-sensitive networking, or TSN, to be used for Ethernet-based fronthaul. TSN is achieved using 4 components for time synchronization, bounded low latency, ultra-reliability, and dedicated resources. Time synchronization uses both Sync-E and 1588v2, where TSN network elements can operate as a boundary clock to pass timing and synchronization to remote cell sites. Bounded low latency will guarantee a not-to-exceed end-to-end latency required for critical applications. The use of frame preemption for long blocks of Ethernet traffic will maintain low latency variation, or jitter, for critical 4G and 5G traffic. Frame replication and elimination over disjointed paths avoids frame loss due to equipment failure. Using these components will guarantee data transport with bounded low latency variation, and extremely low loss. The Open RAN Alliance is driving openness and intelligence in the radio access network. An area of openness is the physical layer 1 low-order processing stack, otherwise known as Lo-Fi Functional Split 7.2. My colleague Stuart had in fact reviewed that in his first couple of slides when going through the different stacks of the actual communication structure. Moving from the BBU in 4G to the 5G RU is this functional split, this Lo-Fi functional split. And in moving this processing function from the hub location to the cell site, the protocol is eCPRI, which is an Ethernet form of CPRI that is much more efficient. Applying this concept to the 4G network at the cell site with Lo-Fi functionality will reduce the CPRI rate over the fronthaul up to 5 times. This means that a CPRI 7, which is a 10 gigabit per second service channel, would be translated to eCPRI operating as low as 2 gigabits per second over the fronthaul span. Implementation of Lo-Fi to the 4G remote radio head, or RRH, will require the radio vendor to open up the format of their IQ data within the CPRI frame. Once the CPRI is translated to eCPRI, the service channel connects directly to the 5G virtualized OpenDU at the hub location, collapsing the 2 networks into one. Finally, this openness and remotely deployed technology, the service provider will have the flexibility of multi-vendor interoperation. So let's look at the midhaul and backhaul sections as well. The midhaul and backhaul of the 5G access network will evolve to an SDN-based network with the dynamic operation, flexibility, and cost-effective capability of virtualized network functionality. The disaggregated MPLS segment router offers this capability where the control plane is in the cloud, where it is decoupled and independent from the user plane. This CapEx-efficient structure or architecture scales out via linear resource scaling. Multiple virtual router instances can share the same network element hardware through cloud control plane virtualization. Microservices are defined in the cloud on a global basis with protocol isolation per router instance. Maintenance and upgradability is simplified through decoupled software from the network element. This disaggregated cloud control plane architecture for the transport router offers better infrastructure utilization versus a traditional router architecture. Let me now hand it over to Stuart.
Excellent, thanks, Joe. So when we move forward with the network itself and looking at the structure of the traffic going over the network, people often talk about time-critical, ultra-reliable, low-latency type traffic profiles. The important thing with the change in the network is that our traffic profiles are actually what's ruling the network structure or architecture of the network as opposed to the historical other way around. So if we have a look at the diagram in the bottom left corner, you've got the ultra-reliable low-latency section. That traffic would be routed because of latency concerns to the nearest CU or DU, being the one in the middle of the PowerPoint slide there. Whereas the enhanced mobile broadband, just to the left of that, that traffic could be routed depending on how busy the closest CU and DU is, could be easily routed to the further away CU and DU on the right, transferring across the NGFI, the Fronthaul, and the NGFI2, the Midhaul areas. So it's quite interesting because all of a sudden our traffic routing is changing or by latency concerns. So the network size also of these NGFI1 and NGFI2 networks themselves have been somewhat broadly defined by the IEEE 1914 standard based on the latency requirements of those rings, because latency is what the concern is. So if we quickly look at that, we can see that, for example, as per 1914.1, which releases ideally in about 3 months with approval, within that standard group, we talk about 10 routers in the front end, each connected to 3 towers with 3 RUs on top of each tower for each sector. We talk about hundreds of gigabits in that NGFI1 ring. Each of them running very likely at 25 gig, but a ring, a DW ring, as Joe just discussed, of hundreds of gig. We move back to the Midhaul or the NGFI2 section of the network. 1914 discusses that as having 8 router sections, in which each of them, it expands out to 90 RUs. Because you're now on the functional split that is most likely option 2, not option 7.1 that Joe and myself discussed slightly earlier, we end up in a situation which it's only about 4 gig of traffic for each of those RUs. And then we end up with, once again, hundreds of gig of traffic going through that. So what we're saying here is the traffic required in the NGFI1 and NGFI2 is extremely large compared to what we're historically used to, and it's based on latency, is the concerns to how that's going to work. So to simplify this a bit, let's break down the picture to what the network structure actually looks like. So from a traffic standpoint, you can simplify it. And you see here, for example, the top diagram here, we have the core network through the mobile backhaul. going into the CU, DU, and RU, which is combined. This is very much like today's network, with everything happening at that one location. In today's network, sure, there's coaxial cable or fibre up the antenna, but it's all centrally located at that situation. So the first picture, much like 4G or even 3G networks. And the second one's a bit more interesting, where in the mobile front haul, it has very stringent latency requirements on it. So in this case, with the RU separated by the mobile front haul into a combined DU and CU, it could be used for very latency critical type traffic that could be enhanced ultra reliable low latency as an example. Where the third diagram there, we talk about having the RU and the DU combined. So the traffic profile for this type of configuration would commonly be used for a massive MIMO or something where each sectors in the antenna need extremely tight timing to them. But back to the CU, the central unit, you have a less stringent latency concern across the NGFI2. Where the last diagram, or line diagram here, is a bit interesting. This is the one that 1914 is pushing out there, where we're having obviously a mobile front haul, a mobile mid-haul, and then into the backhaul. This offers a lot more flexibility in the network design and would be a more cost-effective way for an operator if his traffic profiles would allow that, which will depend on many things such as the population density and so forth. So moving on to the next diagram here, we can see that we've broken it up into what are more traditional views of the network, being the access, the aggregation, and the core. And other words for that are commonly used depending on market or regions of the world is, the cell, the hub, and edge type areas of the network. So it's important to note that the line diagrams across the bottom, for example, the very bottom line diagram, which was the first picture on the last slide, we see that the mobile backhaul, or effectively the core, extends all the way to the access network. And in the top diagram, or the top line diagram, we have an NGFI1 and an NGFI2, or a front haul and a mid-haul network, which is more like today's networks type thinking and structure. But really what it all comes down to is that the demarcation of access, aggregation, and core is basically having to disappear in tomorrow's networks, in the 5G networks. And the reason is quite simply because of latency, and the network will have to dynamically adjust. Interesting enough when I say dynamically, because what will happen is all of these elements we're discussing will be cloud controlled. And so depending on the traffic profile entering the network will have to be dynamic to adjust to work with that. So with that, I'll hand it back to Richard.
Thank you very much indeed, Stuart. Just a quick reminder before we move into the next section. Our Q&A segment will be following the presented slide-based material, so we'll be doing some live questions and answers towards the end of our hour. If you do have a question that occurs to you at any point, just hit the Q&A part of the On24 interface, type in your question, and we'll do our best to get through as many of those towards the end of today's presentation. So, to jump back in, we've heard about some of the X-Haul solutions available and how 5G impacts the core network, but what is vital, of course, is that these solutions map to real-life applications. So now we're going to have a look at how network topologies are evolving to meet those different network scenarios. And I'm going to start off by asking Joe to tell us a little bit more about what Ethernet-based front haul looks like on the roadmap for operators, and then I'm going to ask Stuart to talk us through some of the performance considerations for operators when they're building 5G networks in terms of things like latency, availability, and timing. But over to Joe first of all.
Well, thank you, Richard. An example of an Ethernet fronthaul-based deployment using time-sensitive networking, or TSN, for 4G, 5G, and Ethernet services is shown here. The illustration depicts a CRAN architecture, a centralized RAN architecture of central hub location to multiple cell sites in a point-to-multipoint configuration. The central location is established as a boundary clock, passing timing and synchronization information to the remote cell sites. 4G CPRI service channels are encapsulated over Ethernet as radio over Ethernet transport. 5G eCPRI is already in an Ethernet frame structure, and enterprise data access is passed as Ethernet traffic with preemption, minimizing latency variation on the higher priority traffic, that being the timing, sync, 4G, and 5G services. Remote visibility and performance monitoring is achieved using standard OE&M techniques. The illustration here shows a TSN aggregation and transport architecture similar to the one we just looked at with 4G, 5G, and Ethernet services. However, at the cell sites, there is an additional function using the O-RAN Alliance low-fi functional split 7.2x. The low-fi, or low-order processing physical layer 1 functionality, is integrated into the TSN aggregation and transport platform, operating as a gateway for 4G traffic to 5G distribution units. Implementing the low-fi functional split into the TSN platform at the cell site will translate the CPRI service channels to eCPRI, which is a much more efficient Ethernet form, reducing capacity by as much as 5-to-1 over the fronthaul network for those originally CPRI channels. The low-fi implementation will require the 4G radio vendor to provide openness of their IQ format within the CPRI frame. This low-fi translation of CPRI to eCPRI integrates the 4G network into the 5G network at the hub site through the use of the O-RAN Alliance compliant OpenDU, or Open Distribution Unit. This OpenDU is a virtualized distribution unit, and it integrates the 4G and 5G networks, eliminating the overlay, and along with the low-fi function, offers multi-vendor interoperability from cell site to central location. Now let's look at another use case, which is network slicing as a service, which will require network elements to operate with virtual network functionality. The disaggregated router shown here has a control plane in the cloud and an MPLS segment router user plane in a high-performance programmable platform. As the network slices are defined in the network, virtual router instances are configured in the cloud. Hundreds of virtual router instances can be configured for each network element. The cloud control plane will automate the provisioning metrics using zero-touch provisioning and then push the programming down to the user plane infrastructure. Here I'm showing one network site, but imagine many of these sites configured in a mesh topology, all simplified using this cloud control plane approach. This disaggregated cloud control plane approach offers the ability to scale out, providing multiple virtual router instances per network element and automation interconnecting all the services with required SLAs. As the customer VPN services are provisioned within the network slices, full resource guarantees and isolation in both the data plane and the control plane are administered. Operational costs and complexity is greatly reduced by creating and dynamically managing discrete virtualized networks over a common infrastructure, along with automation. The result is one common infrastructure with multiple virtual networks. Let me pass this over to Stuart.
Excellent. Thanks, Joe. So when we're looking at these network structures, we need to concern ourselves with the latency, and the latency is defined by different groups differently. So I think it's important to be able to see the network Joe's talking about and getting across that network, how we can look at the latency and what are the requirements per the different standard groups. So the first one and the most common standard people talk about most is 3GPP, where the latency of 3GPP is actually from the UE, or the user device, the mobile device, back into the next generation core, which is what used to be called the BBU. So, with a 500 microsecond latency across that network, it's not too bad a latency when we look at it. It's quite open. But then when we move on to the next standard, the IEEE standard, IEEE have turned around and defined it as 100 microsecond, but from the radio unit back into the BBU, or their new naming, ERE and EREC. But that's only, as I mentioned, 100 microsecond. These are all one-way delay. So that effectively means that we've got 400 microsecond across the air interface, but we're quite restricted on the wireline interface. So the next standards group in here, which is IEEE 1914, which is interesting because 1914 has broken it down into those mobile Fronthaul, mobile Midhaul type areas, or NGFI 1 and 2. Another word that IEEE 1914.3, by the way, is ROE, which is almost the same as eCPRI. So ROE and eCPRI are commonly interchanged in that Fronthaul section. But anyway, in the Fronthaul section there, the ultra reliable low latency, we're down to 50 microsecond to the distributed unit, the light blue unit. If it's a dual split, as you can see, the top line of directly from the RU on the bottom diagram to the central unit, the darker blue unit, you've got 100 microseconds total for ultra reliable low latency. So it could be in the NGFI 1 or in the NGFI 2 there, but it's still very restrictive. So it's interesting looking at that ultra reliable low latency. In the IEEE 1914.1, it's 100 microsecond on the wide section across the whole wide section. In the IEEE 802.1 CM, or time-sensitive network, as Joe was discussing, it's also 100 microsecond. And by the way, just for your information, 802.1 CM is heavily, there's a lot of relationships and discussions between the eCPRI group and that relates back, that 100 microsecond, back into eCPRI's requirements as well. And then, of course, the top ones we mentioned before, the 3GPP, also has that same area, but it doesn't divide it the same way. So it's also, just to jump back, down to the IEEE one at the bottom, we can see between the light blue and the dark blue, the distributed unit and the central unit, we have up to 3 milliseconds for enhanced mobile broadband or non-ultra reliable low latency. So interesting to note is the 4 milliseconds for 3GPP enhanced mobile broadband is basically the same as the IEEE. Also interesting to note is 3G, 4G networks have the same 4 milliseconds. So there's nothing new there. Last point on this slide is when we look at the mobile backhaul, It's still at 10 milliseconds. There's no change there. That's the same as today's networks. So it's in line with what we're looking at today. So moving on, another point that these 5G networks is becoming very important as we're moving away from a CPRI-based network to an eCPRI or an ROE, 1914.3 network. We move into a network that is routed. So because it's a routed network, we can obviously not point-to-point like CPRI was predominantly. We end up in a situation that we can reroute, which means that the network elements, we talk about timing of being able to make sure we have enough uptime. So in these networks, we with the 5.9, the traditional telco network rerouting structure, we end up with about 5 minutes per year allowed downtime. With the 5G networks and ultra reliable low latency, we're moving forward now to having only 30 or the 6.9s, which is only 32 seconds per year of downtime. It'll also be interesting because the rerouting time is 50 milliseconds. That's unchanged from a very old standard that was used in SDH or Sonic days. So that's unchanged. So it'll be interesting to see with those ultra reliable low latency how that is, how the elements out there are going to be able to cope with a rerouting situation of the network. And the last thing here I'd like to touch on is another key area of 5G networks, which is network timing. So the whole network is required to be in time for it to work. This all relates back to 5G and the elements, the hand pieces or the UEs, are moving to TDD, time division duplex, which allows them to get better throughput as they switch between antennas or towers, radio units. The issue is, of course, though, that you need very accurate timing at those radio units with comparison to each other. So where that becomes, on the face of it, that would appear to be quite simple. But where the complication comes in is the timing network is not necessarily the same as the NGFI network or the mobile fronthaul, mobile backhaul. It's a structure of the network across the whole operator. So you can have, as you see here in this diagram, the grand master clock at the top, the green clock, feeding two different boundary clocks, which are actually across a different network. So as you can imagine, a car driving along that ultra reliable low latency network there, between the two RUs, the orange and the red RU, it's actually, from a timing perspective, switching to a different fed time. It's the same grand master, but the synchronization across the network has to be accurate enough to make sure that those two are in sync. That's extremely important with the coordinated multi-point, where you have maximum throughput across two RUs. Which we can see in a lot of things, and ultra reliable low latency, it could be extremely important depending on the end use. So the key here will be, or as per 3GPP, is that those two RUs that is shown here, the red and the orange RU, the radio units, need to be within what's called a TAE, a time alignment error, of no more than 3 microseconds between them. So very accurate timing being fed across different networks to two RUs. It's not the whole every RU in the network, it's just any RUs that a mobile element could switch between. But when you expand that out, you very quickly get to a position where it's almost covering the full network. So timing is one of those things that hasn't had to reach all the way out to the mobile before. It was done in a different way, but now it's across Ethernet. One of the weaknesses of Ethernet is transferring timing, hence the newer standards with synchronous Ethernet, and hence how this timing structure needs to get all the way out there to these end radio unit devices. It'll be an interesting discussion with a lot of people, I think, moving forward. With that, I'll hand it back to Richard.
Okay, thanks very much, Stuart. A great overview of different deployment scenarios from Joe and Stuart there, and some of the ways in which X-Haul solutions are evolving to meet the challenges of 5G. So now we're going to hear from each of our sponsors with a brief segment outlining their organization's portfolios for this particular environment. And I'm going to start with Stuart. So, Stuart, go ahead.
Excellent. Thanks for that. So we'd just like to quickly discuss here, Anritsu is a global supplier of test and measurement equipment, and obviously a very big RF as well as wireline and wireless. So on the wireline side of it, we have one product that basically covers it all, the Network Master Pro, which the diagram here is of. And we talk about, obviously, we can do testing across the mobile Fronthaul, the mobile Midhaul, between those elements without any problem there. Back to all the standards, whether it's eCPRI, whether it's ROE, which is 1914.3, or whether it's up to the latency requirements and so forth, the 3GPP or IEEE. On top of that, if you wanted to do timing, of course, we can use the same piece of equipment to then do testing of the timing. That can be plugging in a GPS basically to our unit and get things such as 1 PPS or packet TE timing across the network for different types of timing networks, an FTS or a PTS, partial or fully supported network. As well as if you wanted to, you could go from the Network Master Pro to the core, or you could use another Network Master Pro as your Grand Master as well. Lastly, but not least, I'll just touch on that we also cover the core network, whether that be the SONET, SDH, OTN, or of course Ethernet type areas, and all the relative standards across that. So all I've really got to say there is a single solution to cover all the transport needs. With that, I'll hand it back to Joe.
Well, thank you, Stuart. Fujitsu has an advanced 5G transport ecosystem, and this solution is based on our experience as one of the largest C-RAN and backhaul deployments in North America. Advancing to 5G offers Fronthaul, Midhaul, and backhaul edge transport utilizing 4 powerful technology areas. TSN for high-precision timed 4G, 5G, and Ethernet transport up to 100 gigabits Ethernet. O-RAN Fronthaul gateway with Lo-Fi split 7.2 integration. Cloud control plane, which simplifies and expedites complex network implementations using virtualization, resulting in ultra cost-efficient service scaling and purpose-built routing. The purpose-built disaggregated MPLS segment routers provide hundreds of virtual router instances per network element. This Vichora SDN solution for SmartHaul provides a comprehensive modular software suite that enables CSPs to build and operate a hybrid physical and virtualized X-Haul network. The solution is based on network expertise, specialized partners, and the best of open source technologies, utilizing modern approaches such as SDN control, open source software, model-driven architectures, and microservices to enable CSPs to manage these environments cost-effectively. The framework encompasses software-driven defined network control, network planning, wavelength design, service fulfillment, and assurance for physical and virtual network functions. Our solutions are designed to support multi-vendor, multi-domain networks with flexible workflow design and network modeling. Finally, our Fujitsu services team can design, integrate, and deploy and provide ongoing managed services for your network. Let me pass this back over to Richard.
Okay, thank you very much. So just before we head into our Q&A, I'm just going to spend a minute or two recapping and reiterating some of the points Stuart and Joe have made. Final reminder to get your questions in to us. We've got some great questions in from you already, so we'll zip through and get to the Q&A. Stay tuned. So we heard that 4G to 5G evolution and the deployment of new radio for network density is going to drive major changes in transport networks, some key challenges in terms of blending legacy and new 5G networks, whilst eliminating the need for overlay. That's going to be a challenging environment in terms of criteria such as capacity, latency, timing, availability, etc. The CPRI frame format can't be used for 5G networks, but we've heard about Ethernet as the foundation of a more flexible and future-proof solution, packet-based Fronthaul using time-sensitive networking, which enables reliable and deterministic real-time communication. We talked about disaggregated cloud control plane and user plane operation and how this enables network slicing as a service and what that means in terms of programmable service creation and provisioning. And lastly, we heard about the vital role of X-Haul performance benchmarking and the availability of single solutions for transport testing, and really the importance of working with vendors that have a long-term roadmap for X-Haul as it evolves into the 5G era. So with that, we're going to conclude today's presented material, and we're going to go into our Q&A. We've got a number of great questions lined up, so without further ado, I'm going to pitch straight in and start asking some of our audience questions. So one of the first ones I want to get to starts with a bit of a clarification. It's regarding the IEEE 1914. Is that the same as NGFI? And what about ORAN? Is that a competing Fronthaul spec to 1914? Stuart, you've talked a little bit about standards. Joe, you've talked about them as well, and the ORAN Alliance, so I guess both of you are going to have something to say about this. Stuart, could I ask you to pitch in? Give us a bit of clarity about what 1914 means.
Yeah, sure. 1914, I'm one of the guys on that group. It's a great group of people, but basically 1914.3 is the standard for the frame structure, which is almost the same as eCPRI. They take up about the same amount of overhead, so they can be interchanged. They are, I guess you could say, competing standards, which is, I believe, a good thing to have multiple standards out there to move forward. Also, so you mentioned there with regards to ORAN, 1914.3 is working closely with ORAN. We've had several liaison letters between the two groups in which we're looking at ways to move forward and continuing to work together. Basically, ORAN is the layer above. ORAN, I guess you could say, is sitting on top of 1914.3 standard or on top of eCPRI. ORAN is capable of using either. So they're not competing at all. They're different layers within the stack, and both CPRI and ROE or 1914.3 are interchangeable at the bottom end. Joe, do you have anything to add?
Sure. I think Stuart handled most of that, but just to clarify some of the points, going from originally there was the XRAN. The XRAN group was looking at 1914 and the eCPRI cooperation and merging those two groups together into an open environment for the RAN configuration. And that moved from XRAN to ORAN. So ORAN is somewhat related to IEEE 1914 as well as the CPRI cooperation group of radio vendors. So there's not so much of a competing, but more of a complementary environment between all of them in terms of that evolution of groups.
Okay, thanks very much. Okay, so next question is around time-sensitive Ethernet. Joe, I'm going to turn to you for that one. Any kind of test results around time-sensitive Ethernet in Fronthaul? How's it performing?
Well, in time-sensitive Ethernet, we have completed a series of POCs. And through these POCs, we've determined that time-sensitive Ethernet has worked well in terms of establishing a boundary clock from a grandmaster. So this is where, in terms of clocking and synchronization hierarchy, there is a grandmaster clock. It's passed over to different centralized points that then fan out to cell sites. Those centralized points become boundary clocks. There are secondary boundary clocks in the event that one were to fail. So there's a resiliency that's established there. But using SYNC-E and 1588v2 has been what was used in those POCs, and it has worked well.
Okay, thank you. Stuart, anything you want to add, or can we move on?
No, I think we move on. There's so many questions.
Okay, great. Okay, the next question is about ROADMs, which, forgive me if I've got this wrong, but I think is reconfigurable optical add-drop multiplexers. What's their role in midhaul and backhaul? Would it be, for example, to be used to create mesh? I'm going to come to Joe on this one. Fujitsu's an optical vendor. Tell us about ROADMs.
Sure. Thank you. So ROADMs typically are in part of the core network. That is beyond the backhaul, although the backhaul in 5G, backhaul and core are sort of blending together into one. So in terms of a ROADM network interconnecting many high performance, high bandwidth routers using a ROADM technique, which is essentially wavelength switching technology between and among them, which can be easily reconfigured based on different requirements, demand requirements within the network would be implemented. So more in the core backhaul area of the 5G area, not so much in the midhaul, although you could scale up in the midhaul at some point and maybe even have some form of wavelength switching that would occur there as well.
Okay, thanks very much. I'm going to try to get through a couple of quick questions before we get to the top of the hour. Stuart, one for you, if I may. Is it a correct takeaway that 3GPP, IEEE 1914 and 801 do not conflict with each other? Is that correct?
Yeah, basically no. I mean, time-sensitive networks, I mean, once again, IEEE 1914.3 or .1, both of them in this case, are having communications or liaisons with the time-sensitive networks, 802.1, and there's lots of communications going on there. There's been some discussions that's allowed us, as the IEEE group as a total, 1914 and 802.1, which have made some suggestions between groups and other groups taking care of it. So all these standards groups are working very close together. I guess from the outside looking in, it doesn't appear. It appears like they're different directions. But once you're working within these groups, it's very common that most of the guys sit on multiple boards, and there's a lot of communication between everyone. So it's all working well at the moment, and there's no real conflict. It's a good situation within these standards at the moment.
Okay, thank you very much, Stuart. I'm afraid that's time up, and that's all the questions we can take. So thank you very much for all of those questions, and apologies if we didn't get to them live. We will try to follow up after the conclusion of the webinar in the coming working days and try and get some answers to you offline. But for now, thank you very much for joining us. I'm going to hand back to Alan Tatara, our host, to wrap up. Alan.
Thank you, Richard. And I also want to thank everyone for submitting your questions and comments and for participating on the webinar today. We do appreciate that. I want to thank Richard for leading our discussion today, as well as Stuart and Joe for this engaging and in-depth discussion. So an archived version of this webinar will be made available shortly, so feel free to come back, view the session again, or even share it with your colleagues. Now, you will see a short survey pop up at the conclusion of this webinar, so please take a few moments to fill that out. We'd love to get your feedback. And please continue to follow us on Twitter and LinkedIn for information on future IHS Markit Technology Group webinars. So again, thank you for joining us, and have a great rest of your day.